We're now moving on to the concept of a torque in the equilibrium unit, and for this very first question, we need to find the unit for a torque. So torque takes a symbol tau with a sideways t, and that's going to be equal to the force times the distance. Now force is measured in newtons, and distance is measured in meters. So the units for a torque are newtons times meter. So option number B. Moving on to the second question. So which of the following is a torque expression? Okay, so just like the previous question, torque takes the symbol tau, and that's equal to a force times a distance. Now regarding the force, force is just a number, right? So throughout this particular chapter, we're going to be dealing with some angles as well. So for example, we could have force, and that could be at a certain angle like sine of 30 degrees. And then we're going to multiply that by the distance. Now this part right here, this is just a number, right? So it's still all related to the force. So this is still force times distance. So the best option here is going to be option letter D. So this part right here, although it is a force times a sine of an angle, this is still a number. And obviously the distance, that'll be a number. So you're still multiplying a number by a number. All right, so force times distance regardless. So option D is the best answer there. All right, for the next question, we do have a definition question. So which of these is an acceptable definition for rotational equilibrium? So when we're dealing with rotational equilibrium, we want to ensure that we have a few things that are being met. So most of the times the object will be at rest, and we don't want to have any angular acceleration going on. So that kind of means that the forces in the clockwise direction is equal to the sum of the torques in the counterclockwise direction, which is something that we're going to look into more a little bit later on. So we want to say that the sum of the torques is going to be equal to 0, and then that's also going to mean that the sum of the torques clockwise is going to equal to the sum of the torques counterclockwise. So these are some of the ideas that we're going to see later on in this particular chapter. So the best option here is going to be option number A. So this is the sum of the torques being equal to 0, and that generally means that your object is not going to be moving because we're going to be canceling out the angular kind of forces that are acting on that object. And something like this kind of has to do with translational equilibrium. Okay, let's continue to move on. So another concept that will come up in this particular chapter is concepts like forces going in the counterclockwise direction and the clockwise direction, and we'll build towards that particular concept as well. So in this next problem, which of the following situations does a force produce a counterclockwise torque around the point P? Okay, so when we're dealing with counterclockwise and clockwise, I want to say that this direction here, this is kind of like your clockwise direction, and your counterclockwise direction is going this way. So this is your counterclockwise direction. Okay, so we want to look for a force that kind of exhibits that kind of behavior here. So this is your point P, and for option B, it looks like this force is being forced in this direction. So this is kind of like your clockwise direction. And then here's your point P, and this force is going in that direction there, around that point P. So this is the clockwise direction. In this case, I guess the force is just going in a straight vertical direction there, so it's not rotating at all. It's just kind of going up in that upwards direction, I guess. And for option number A, here's your point P there, and this force is kind of creating that angular direction here, and it's kind of going in this direction. So this is the counterclockwise direction. All right, so that kind of matches what we're trying to do over there, right? So the best option here is option A. That force produces a counterclockwise torque around point P. Okay, let's continue to move on here. Another kind of a theory-based question here. So we have a meter stick in all four situations. So here are your 4 meter sticks. And for this question, the meter stick, we're actually looking at it from above. That's kind of key here, right? We're looking at it from above. Okay, so keep that in mind when you're kind of looking at these meter sticks. And the meter stick is sitting on a table, and then there is subjected to 2 forces of equal magnitude as shown, in which case would the meter stick be in rotational equilibrium. So when we're talking about rotational equilibrium, that generally means that the torques are balanced, meaning that the sum of the torques clockwise is equal to the sum of the torques counterclockwise. We haven't really talked about that concept too much, but let's just say that when we're dealing with rotational equilibrium, we're looking for things that are at rest and things that have no angular acceleration here. Okay, so if you don't have any angular acceleration, we're assuming that you're not moving. Okay, so if I look at these options here, I would say that since we have these forces kind of acting in that direction, that's going to create some angular acceleration there. So we want to eliminate options C and D right away. And because we're looking at this from above, it seems like we have a force of gravity here as well. And it kind of means like this is kind of trying to go into the clockwise sorry, it looks like these forces are trying to create this clockwise direction, so we could have some angular motion there. So we want to eliminate option number A as well. When we're looking at option number B, the force of gravity is kind of in the middle there. This means we're kind of going to the left and to the right when we're looking at above. So we don't have any angular kind of movement in this particular case. So option number B would be the best option, where we're in this rotational equilibrium, where the object is trying its best to be at rest, and that's because there's no kind of angular kind of movements happening in that particular case. So option B would be the best one for that one. Okay, let's move on to some other questions here. Okay, so now we're going to get into some more calculation questions, or we're starting to build towards some calculation questions here. So in this next question, it states that a force, which is this force right here, is used to apply a torque to a beam as shown. And I guess we have this fulcrum right here, which is kind of like the point P. So this beam is going to rotate kind of around that point P there, and the question is, which of the following is the correct equation for finding the torque about the fulcrum due to this force here? Okay, so step one, I want to say that a torque is equal to a force times a distance. More specifically, the force that we want is kind of like this perpendicular force times d. And that perpendicular force, sometimes I will use different kinds of notations, but sometimes it's like the force in the vertical component, and then we times it by the distance from that point B, from that point P there. Okay, so in this particular case, let's look at the distance here. So I guess that force is being applied across this distance here. So this distance in all three cases is denoted by the letter L. So I'm going to erase the D's now, and I will write the letter L there. Okay, so we're kind of halfway there. And then once we look at the force here, this force is kind of going in this angular direction there, right? So what that really means is we have a horizontal force in the horizontal direction, which I'll denote Fx, and we also have a vertical force, which I'll call Fy, and sometimes this is kind of like your perpendicular force. But I'll kind of leave that as the vertical force Fy for now, and that's going to be equal to the angular force, which is F. Right? And since the angle is touching this angle right here, I guess this is your adjacent, right? So and this is kind of like the opposite side here, so it's going to be F times sine of the angle, which is so similar to how you would set up the kind of the vertical and horizontal velocities when you're dealing with projectile motion, and this is really the exact same concept here. So what we need is the force times sine of the angle. So this whole expression right here, Fy, that's equal to F, the force, times sine of the angle, and then we're going to multiply that by the distance. And that is the torque that we have due to that angular force there. So option letter D would be the best one here. And for sure, we're going to be working with this concept a little bit more when we're dealing with our calculation problems. Okay, let's move on to some calculation questions now. Let's take a look at our very first calculation question now. For this next problem, we have a uniform 2.4 meter long beam. So this whole length is 2.4 meters, and it has a mass of 25 kilograms and is kept horizontally by a force F. Okay, so the force F here is kind of going in this direction right here at 30 degrees. And because the beam here, the 2.4 meter long beam has a mass of 25 kilograms. Right in the center, we have a force of gravity that's going in the downwards direction. Okay, and in order to keep this beam in this horizontal position here, the force in the red direction, which is right here, has to kind of go in that upwards direction, but it's also, moving to it's kind of that northwest direction there, and this F has to be big enough to kind of keep the beam in that horizontal position, and we want to find the magnitude of the force F so that this beam here is in rotational equilibrium, meaning that it's at rest. Okay, so the concept that we kind of need to kind of put together is this idea over here of a torque being equal to 0, and that literally means that the sum of the torques clockwise is equal to the sum of the torques counterclockwise, and that will keep the beam in rotational equilibrium, which means the beam is not moving because all the forces have been balanced. Okay, so let's go back to our free body diagram here, and let's kind of break this down here. So we have this fulcrum right here, and we call this like your pivot point or point P, and the blue and the red vectors or the forces here are going to be acting around the point P. So this FG is kind of going in the clockwise direction there, right? And this F here, it has two components. There's a force in the vertical direction, and there's a force in the horizontal direction. And this vertical force here, Fy, that's going in the counterclockwise direction. And what we're trying to say here is that this counterclockwise direction and this clockwise direction, they're canceling each other out so that the beam can be kept in that position. And that's what we mean by rotational equilibrium. So what we're trying to say is that the torques are equal to 0, therefore the clockwise torque and the counterclockwise torque are going to be equal, thus creating the rotational equilibrium, and that will keep the horizontal beam in this current position here. Okay, so what we're going to do here is I'll call this torque 1, and I'll call this torque 2. Okay. So despite all these forces here that are kind of drawn, the main kind of forces that we really need, let me kind of erase this, we want to make sure that this vertical force right here is equal to this force down there, and that will make sure that the beam is in this rotational equilibrium there. Okay, so this is going in the clockwise direction as mentioned, so we'll call this torque 1. So torque 1 has to equal to the second torque, which is denoted over here. This is your second torque right there. Okay, so that's what I mean. This is what we mean by rotational equilibrium. And it's very important that you kind of set up one of these arguments here to show that you understand that the beam cannot move because we're in rotational equilibrium, and that's because the torques are all balanced. Okay, so what is the definition of a torque? It's really the force times the distance. And this torque is also equal to force times the distance. Now the force that's acting on the very first torque is really the force of gravity times its distance. And for this force over here, the force that we really want is this vertical component there, right, Fy. Now in order to find Fy, that's going to be equal to this angular force times sine of the angle, sine of 30 degrees. Which is covered in some of the previous questions already, but very similar to the projectile theory questions. So we'll write this as F times sine of the angle times its distance from point P. Okay, now let's go back and let's figure out how we can plug in the numbers in here. So we have a 25 kilogram mass, and this force of gravity is actually halfway to the point P. So if this whole beam is 2.4 meters, then halfway of that is going to be 1.2 meters. Okay, so if I want to calculate this entire torque right there, but due to the force of gravity, because the mass is 25 kilograms, what we can do is we can calculate our force of gravity being mass times the acceleration. So the mass here is going to be 25. The acceleration due to gravity is 9.80. And that force is actually 1.2 meters away from the point P. Alright, so now if I attack the right hand side, the force is the magnitude that I do not know, but the angle is going to be 30 degrees, so it'll be sine of 30 degrees. And this whole force, Fy, it's a grand total of 2.4 meters from the point P. So we'll times that by 2.4. Okay, and there we go. Now we've set up our rotational equilibrium problem here, and our goal is to solve for capital F. Okay, so if I go ahead and I multiply these numbers across here, 25 times 9.0 times 1.2, I get 294. And then on the right hand side, I get F times, well, and if I multiply sine 30 degrees times 2.4, I get 1.2. And our force here is going to be 294 divided by 1.2, and that's going to give us an answer of 245 newtons. Okay, good. All right, let's go back to the beginning again, and I know there's a lot of colors here, so I'm going to kind of erase all of this now. So we just went ahead and found the magnitude of this force, and that magnitude of that force has to be 245 newtons. Okay, so if the force is 245 newtons in that direction there, then this entire beam is going to be balanced. And just before we kind of conclude here, I just want to note that the force of gravity, which is at the halfway point here, it was force equals to mg. And if I take my 25 kilograms and times it by 9.0, ironically, we also get 245 newtons, right? So yeah, it turns out that the magnitudes in this case, they were actually equal, which is not always the case, but those numbers that we need to kind of keep this particular beam in check here. And if you want to find your Fy component, it's going to be 245 times sine of 30 degrees. And 245 times sine of 30 degrees, that's going to give you about 122.5. And you can also find the Fx component too, which I won't do here, but it would be 245 times cos of 30 degrees. So those are the different kind of forces that are acting together. So even though this is 122.5 in that vertical direction, and this is 245 newtons, it's still going to be balanced because we have other forces acting on that particular point there. So this is the whole idea of rotational equilibrium. Let's take a look at one more calculation problem to finish this homework video guide. And for this problem, we have a crane that's used to lift one end of a uniform 50-meter long pipe with a mass of 730 kilograms as shown in the diagram below. And we want to find the minimum force of tension in the crane cable to just lift the end of the pipe off the ground there. Okay, so here's your here's your uniform long pipe right here, and since it weighs 730 kilograms, it does have a force of gravity acting in the downwards direction. And there's also a force in the cable here, force tension, so I'll call that the force in the cable right there. And we want to find the minimum force in this cable right here, right? So this is a rotational equilibrium problem here, and what we're going to do is we're going to establish a pivot point. And a very good strategy is to kind of put the pivot point at the very far end of your beam. And the two forces, the red force and the blue force, are going to rotate around that pivot point. Okay, so your force of gravity is kind of going in this, I guess this is the counterclockwise direction. And the force in the cable is kind of going in your clockwise direction because we're referencing to this particular point P there. Okay, so since this is a rotational equilibrium problem, because we have forces going in the clockwise and counterclockwise direction, we want to state that at the pivot point, we want to say that the sum of the torques are equal to 0. All right, so that literally means the torques in the clockwise direction are equal to the torques in the counterclockwise direction. Okay, so we'll call this, I guess we'll call this T2 because tau 2 because it's in the clockwise direction, and we'll call this torque 1 because that's in the clockwise direction, right? So we're dealing with torque 1 on the clockwise side, and we're dealing with torque 2 on the counterclockwise side. Now torque is really equal to your force times your distance, and this is going to be equal to your force times your distance. Okay, Since the red force is dealing with this cable cord here, we got to find, we can label that as F, and this distance right here, the distance to the pivot point, is going to be the full length of 15 meters, right? Okay, so this distance right here is going to be 15 meters, so we have F times 15, and on the other side we have the force, which is your force is going to be Fg, right? So technically this is Fg, but the force of gravity is the same thing as mg, right? Times that distance, and we'll create one more line here, so force times 15, and the mass right here, we're dealing with 730 kilograms, right? So it's going to be 730 kilograms times 9.80, and remember this particular weight, the force of gravity is always halfway to the pivot point, right? So it's half of 15, which is going to be 7.5. And with that, we have enough information here to solve for capital F here, which is the force in the cable there. So if I go ahead and go to your calculator right here, it's going to be, well, if I just multiply all that out, we'll get 53655, and then we're going to divide that by the 15, and then we do have a force equal to 3,577 newtons. So that's the amount of force that we need to keep that pipe on the ground there. Okay, so if I go back and just erase some of this now. Okay, so we just found that this force has to be 3,000. Whoops. It has to be 3,500.